what are recurrent neural networks and why we use them. So in this session, we will cover all the details about recurrent neural networks, like what is a vanilla RNN recurrent neural network, what is its structure, and how is it trained. We'll also see some of the challenges facing these type of networks and how are such challenges alleviated from these networks using something called as LSTM and something called as transformers. Finally, at the end of this session, we will go through a exercise video, which will be a small lab, and we'll see some code examples in that.
In the first session on multilayer perceptrons, we actually talked about something called priors or inductive biases. So in here, what I mean by inductive biases is that what kind of structure is our model encoding in the network itself, which takes some advantage of the data. For example, you can see that in case of convolutional neural networks, the nearby pixels have more say in what the convolution will output than pixels which are farther away. So in a similar way, what kind of biases are taken into account in our model so that it can do well on a given task? For example, in case of recurrent neural networks, we assume that any data that came just before the current time step or any data that comes right after the current time step is more important for making a decision at this point in time. Or you can also say that another inductive bias is that we use word as a complete token or as a token in NLP, but we don't use characters very frequently. We don't use alphabets or characters very frequently, but we rather take the whole word, and that word forms the unit. Like one pixel, a word forms one unit in NLP. So we discussed about how RNNs and CNNs have some kind of structure in their data, and these exploit this structure. So what kind of structure does RNN exploit, or what kind of data do we feed into RNNs? So we basically feed sequential data into RNNs, and sequential data is nothing but something like a sentence which is having a sequence, and the main idea is that the words which come close together are more relevant to the meaning of each other than words which are very far away, and we read them up also left to right or right to left and in a sequence, right? Similarly, speech also is a sequence, and videos are also sequence. We have a past, present, and future in each of these elements, and there is a time dimension. So all this sequential data is what an RNN helps us to model. Now, humans, how do you understand sequence? We basically understand a sequence by remembering what has happened in the past. So we use the past to understand, and these RNNs, they also have something called as memory. The RNN actually uses this memory internally, and it uses this memory to basically store what has happened in the past and keep some context of the past and use that to make sense of whatever data comes out of the current time step. So we also want to see what are some of the applications of RNN before we go deep into why an RNN is required. So some of the applications of RNN are speech recognition. Basically, whenever you call to the Alexa device and ask it a question, that gets transcribed into text through an RNN, and then again the response is sent back to you. Similarly, machine translation, wherein Google Translate or Amazon also translating one page which is written in English to a different language. All those are machine translation, also depends on RNN. So there are a lot of applications of RNN. Question answering is also an application. Like if you have a question, then an automated RNN can read the question and then answer it based on the product details. So how does an RNN differ from a multilayer perceptron or a CNN? So in case of multilayer perceptrons and CNNs, there is a single input and the network is one network and it processes and gives one output, like classification result of whether an image contains a cat or a dog or not. And also similarly, classification results for tabular data and other things. But in case of RNN, there could be multiple variations. Like for example, it could be one to many, like for example, videos or for example, translations. It could be many to one, like sentiment analysis. It could also be many to many, and it could also be many to many in a little different form, which is direct generation. So let's talk about one application like many to one. Sentiment analysis, which takes in a sequence of words and then tries to make some sense of what the overall sentence is, like is it expressing happiness, sadness, or is it expressing some dissatisfaction in the product that has been sent out to the customer in the review. All that comes under the sentiment analysis, wherein we are looking for just one output, which is the sentiment of the sentence. Movie reviews and IMDb reviews also would come into the same place, and they also have been classified into positive or negative. Similarly, there can be one to many also, like for example, if you have an image and that image needs to have a caption and you are using a RNN to generate caption from an image. Then for example, this image here, you would want a caption which says black and white dog jumps over the bar. This is a pretty appropriate caption, and it would basically use an RNN inside which takes the image and then generates the caption. Similarly, there could be applications wherein it is many to many. For example, machine translation is a direct example of that, wherein it takes a sequence in one language and then outputs it in different language. Similarly, there could be another application of many to many, which is a little different from the previous one. Here, what happens is that you have a frame coming in, which is, let's say, a game of football, and you have the ball here and some players chasing the ball. You may want to annotate where the ball is and who is chasing after it. So that kind of processing would basically also be a many-to-many processing, but it will be done frame by frame. So you don't wait till the end result and do it. Like in this case here, you don't wait for the end result and do it. You do it directly right after that frame itself. But you also keep some historical context for helping in detecting the ball. For example, here the ball is pretty blurry. A previous frame could help us determine that this ball was kicked by this guy. So let's look at how the RNN actually works and what the RNN exactly does internally. So RNN is usually nothing but a equation which combines three weight parameters, and we had discussed how these weights are multiplied with inputs to give some result in the multilayer perceptron section. Here I want to basically kind of give you one important idea about RNN and about any deep learning model, for example, right? So what happens is PyTorch or any framework like TensorFlow, these frameworks can compute the backward gradients if you are able to write the forward propagation, right? So if you can write the forward logic, then they can compute the backward gradients, and using those backward gradients, back propagation, you can then train the whole network. So the chain rule and the back propagation all is taken care of by the framework itself. What you have to do is you have to know and understand the forward propagation and modify the forward propagation accordingly for your problem statement. For example, in one of the problems like many-to-many application of RNN, right? Like the one we saw here. In case of this many-to-many application, you will have to write a forward propagation appropriately, which takes in all these words sequentially and then is able to generate the result in a different language. But once you have written the forward propagation, the backward propagation can train this network appropriately. So let's take a look at how the forward propagation of RNN looks like. So don't worry about this equation. We will cover how this comes into being. Just notice that there are three weight matrices here, this one, and then these biases. So the RNN receives an input, and at any time this xt input, then it gives an output which is y here, which is ht at any point of time t. And in case of CNN, that is all you do. But in case of RNN, you have an input xt, you give the output yt, but there is also a feedback loop. Now let's look at how that feedback loop actually works. So here you can see that you get the input xt, you do something with it, and you give the output yt. And there's a feedback loop. Now let's look at how the feedback loop works. So we basically unroll the whole RNN throughout the time, and then we look at the forward propagation. So at time t equal to 1, it will basically take the input multiplied by weight matrix. Then it will generate the hidden representation. The H is for hidden representation at time equal to 1. And then again use another weight matrix to generate an output, another weight matrix to generate the next hidden state for H2 for time equal to 2. So basically you can see that the operation is such that the RNN uses three weight matrices, takes the input, generates an output, and also generates the hidden state for the next step at the next time step, right? And then again in that next time step, again the input comes, hidden state is used, output is generated, and a new hidden state is created. So this process goes on, and that's how the RNN forward propagation works. So you can see that overall the equation looks something like this. So this is the sigmoid function, and this is the nonlinearity that we use in case of RNNs, which takes in basically a weight matrix multiplication of previous time step hidden. For example, here this guy will be multiplied with a weight matrix, and then the input is also multiplied with the inputs weight matrix wx, and that is added and then passed to the sigmoid layer. So basically input multiplied with a weight matrix, previous hidden multiplied with a weight matrix, passed to a nonlinearity, and that giving the output, right? And this keeps happening continuously. So overall, if you unroll the RNN, this last time step will be something like a deep chain of these inputs and previous hidden states being multiplied together. All right. So let's kind of look at what is the parameter sharing in RNNs. So basically you can notice that there is three matrices, right? W, HY, WHH, and WXH. All these three matrices have specific roles. Now, are these different from these? Not really. All these weight matrices are same actually. They're all same. They're shared across time. Basically, the weight matrix remains the same, and each time step, the input is multiplied by the same weight matrix. Similarly, for the hidden also, it's the same, and even for the output also, it's the same. The weight matrices are all shared across the time, while the input keeps varying throughout the time steps. The hidden state also keeps varying. Now you want to calculate the loss function also for an RNN, and how can we do that? Like for example, in case of let's say something like this video networks, right? Wherein we had a video where one frame of video came in each step. For example, here you can say that x1 is one frame of video, x2 is one frame of video, and so on. Now each step of video is coming in, and within the video we have to do some annotation. So if we successfully did the annotation, then the loss here will be low, otherwise the loss will be high. So what we do is in each step, there is some loss computed on each time step, and that will work for the video networks, right? Like in the second frame also we have some loss, in the third frame, and all the frames we have some loss based on whether we could recognize whether the object is present in the video and we correctly recognized it or not. We sum up all the losses and basically that becomes the total loss of the RNN. So let's visualize the unrolling once again in a little bit. As you can see, this keeps repeating continuously over each time step, right? So the RNN itself remains the same, only the hidden state and the data changes. It keeps remaining the same, but the data and the hidden state changes and goes to the next step. Similarly, once again, another representation. The words are basically changing, the input words. The hidden state also changes, but the RNN remains same and is just reused at each time step, and the RNN is composed essentially of 3 weight matrices. Now, the way that this RNN's loss is calculated is also called as back propagation through time. So what we do is we forward through the entire sequence, and at the end of the sequence, we compute the loss. That loss we discussed earlier, wherein it could be frame by frame loss, or it could also be that at the end of the sequence, you will have just one loss coming from here in case of sentiment analysis. And then that loss is back propagated through each of these nodes. Basically, the weights are shared, but back propagation will enable us to compute at each time point what was the contribution to the error, and then that will be used for upgrading the weights. So we will take a small example here, like for example, how do you predict the next word if or the next letter, for example here, next character in a word, and how can you do that? So for example, our training data will be this word hello, and we will do a one-hot encoding basically to denote which letter is incoming, and these letters here this way will be represented as one-hot encoded. Next, this one-hot encoding. Now, the reason for one-hot encoding is we cannot feed anything other than numbers to the neural network. It is essentially doing matrix multiplications, and as such, feeding letters is not possible. So we have one-hot encoded them. Next, what we do is we will train the RNN to predict the next character. So it takes in this, it multiplies the first character with the weight xwx, which is the weight to be multiplied with the input. It produces a hidden state, and next with that hidden state it also produces an output by multiplying the hidden state with the hy why matrix, and that produces our output. The output is then decoded and we get the next character. Now this next character will be fed along with the hidden state into the network again, right? So this E is fed through here into the network along with the hidden state, which WHH takes care of, and the hidden state here multiplied by WHH comes here. Then that is used again in the same form as before, and that predicts the next letter. Something like this. And finally, the loss is basically whether I predicted each of these letters correctly, and that's the loss function here. So how do we basically test this? So for testing, what we do is we basically start with something like first letter, one letter, and then we try to get the next letter, right? So whatever the next letter is, we do a softmax or a just normalize it by doing a softmax normalization distribution. We get the next letter, and then we feed the next letter into the RNN again, along with the hidden state from here. So we keep doing that. We keep feeding the next letter that is generated in the previous time step, continuously into the RNN, and that helps us generate the overall text. So one thing, this thing is basically called as autoregressive generation. So autoregressive basically means that you are taking the previous time step and generating the next, and you are taking the previous time step result and generating, using it as input to the next time step for generating again. All right, so RNNs suffer from something called as forgetfulness or long-term information problem. So what basically happens is, if you notice that the RNNs keep taking the input at each time step and adding it to their hidden step, hidden state, and every time step, what would happen is that the input which came pretty far back will keep getting smaller and smaller representation in the hidden state. So for example, what here, which is represented by the color black, becomes pretty small as you keep going ahead, right? And that is one of the problems wherein the RNN will completely forget what the sequence, the initial part was. Like here, there is a sentence, right? These movies were directed by very famous directors and a lot of money was spent over many years. As a result, they are very impressive. Now, what does this they refer to? They could refer to these movies, or they could refer to famous directors. Now, since we have a good long-term memory, so what we are able to determine is that they refers to these movies here. But an RNN may make the mistake that it refers to famous directors simply because it is forgetful and it forgets this older context. So we have some new kind of networks which are basically called as long short-term memory networks, and these networks enable us to make sure that the forgetfulness problem is minimized. So we basically change the major part of the network, which is the RNN, into a LSTM. LSTM network has basically 4 different gates. So basically these 4 gates are enabling the network to kind of remember more, and it also has a memory cell wherein the information is stored. So the 4 gates of the network, there is an input gate which takes in the input, and its responsibility is to basically modify the input in a way to be used within the network. There is a forget gate which is responsible for determining what information to keep and what information to remove from the memory cell. There's an output gate which finally takes all these things and makes an output. And then there is the memory cell, which is basically storing the context from the past. Now, I want to get into something else, which is called as bidirectional RNNs or bidirectional LSTMs. So before we go into the bidirectionality, let me just elaborate a little bit on LSTM. So LSTM networks basically come with a lot more parameters than RNNs, and as such, while they are able to remember context long term, but they also are more expensive to train. And as such, if let's say the context that you care about is just a few time steps back, like let's say if your sentences are just 16 words or 32 words, then an RNN will be sufficient. While if you have really, really long sentences, like let's say 256 words or 512 words in a whole essay, then in that case, RNNs will have forgetfulness problem, and it is better to use LSTMs. Now, another thing to note is that LSTMs, RNNs, both are directly available in PyTorch, and you don't have to hard code these equations yourself, but rather the framework again helps you do it by default. So, okay, now let's get back to bidirectional RNNs. Now, what are these bidirectional RNNs? Bidirectional RNNs are basically based on the fact that not only the past is important for understanding, but also the future is important for understanding. So in that sense, what the bidirectional RNN does is that it does a forward pass in time, and then it reverses the sequence. Basically, it completely inverts the sequence and then does a pass which is reversed in time. And then the forward and backward reverse directions together are summed up, and that gives the output. So this way, what happens is that at any point in time, you will not only look at the past, but he will also look at the future context and use that in your network. So where can this be useful basically, right? Like in case you are using a network which has to make predictions in the next time step, this is not going to be useful, right? Like if you are trying to predict the next word, this is not going to be useful. If you are trying to predict the something like rainfall, or something like whether tomorrow the sun will rise and shine, or whether it will be rain, if you are trying to predict weather patterns, anything like that which depends on predicting the future, this bidirectionality will not work. But if let's say that you have the whole sequence, like for example you have a IMDb movie review, or you have a uh, sentence, or you have a Amazon review, you have the full thing, and then you want to do sentiment prediction on top of it. In that case, a bidirectional RNN representation is going to be useful, because you have the full sequence. You are not trying to predict the next word or next something, but rather you are just doing something on the whole sequence. So in that case, bidirectional RNNs are very useful. They are more powerful than unidirectional RNNs, which only go through one direction. Think of it as being able to refer back to what you have read, rather than just relying on reading it one time. Like this refers to basically reading it one time and doing it, while if you are doing bidirectional, basically then you are kind of being able to refer it back. So now I use this word referring it back in a loose sense. It is not exactly equal to that, but it's kind of analogous to that. And there is something else which we will go into, which is very, very similar to being able to refer to the past directly, instead of taking a long tour to the past. So that thing is basically the word that we use for that is attention, and I will elaborate on why attention is needed in this example, wherein I'm basically doing machine translation. So machine translation models usually have two parts, a encoder and a decoder. And let's see how a machine translation model works. So encoder basically takes words one by one, as in here. It produces one hidden state. That hidden state is taken by the decoder, and then the decoder decodes the overall and produces a translation. Now notice how this encoder produced only one hidden state from here, right? Like if you see this again, the encoder, it takes in multiple words, and just like how an RNN would do, at the end of the RNN, it produces one hidden state. Now the problem with that one hidden state production is that will not that will suffer from the forgetfulness issue that RNNs have, right? Like there is only one hidden state here, and there are multiple words here. So that hidden state may not represent all the words equally. So because of that, what we use is something called as attention, and I'll show you what attention is basically doing. Yeah, let's look at how attention works. So attention also has a encoder decoder, two models that are doing this, but there's the difference here. All the hidden states are kept, and then they're used in the decoding stage. So let's do this again. So the encoder, even in case of attention models, takes the words one by one, produces a hidden state for each of the word, but then all the hidden states for each word is kept, and they are used in the decoding stage for producing the translation. So all the hidden states from each word is kept, and they are used in the decoding stage. That's the major difference between attention and between a normal machine translation using a encoder and decoder. So in attention, we kept the whole hidden state of each word, and then we did something called as attending to each hidden state, and then that was able to produce the decoded output, which is a translation. Now this attending to the words, each word's vectors or each word's hidden state can also be called as being able to refer back or being able to kind of look and refer back by turning over the pages behind, right? Like, so basically this enables the model to completely skip the forgetfulness issue because it is able to refer back to anything. Even the first word's hidden state is here. So this completely solves the forgetfulness issue, but attention also comes at higher computation cost. So what happens in attention is that you basically compute a attention matrix like this. Like when we were doing a decoding, what we used to do is that whenever one word will come, we will compute how much this word, this output word, is dependent on each of the input hidden states. Similarly, for example, here both am and a both are dependent on this word in the input, right? So this hidden state influences both these outputs. So while giving out these outputs, we compute at each stage how much this word will depend on the words that are in the input. So basically attention does nothing but compute a dependency matrix between the output and the input, and this dependency matrix is then used as a guidance while giving the output, and that makes sure that there is no forgetfulness because all the whole of the input, like all the input words, are taken into account. Now that gets us into a simple question: can I do attention inside the encoder itself? Like we did attention between the encoder and the decoder, can I do attention inside the encoder itself? And yes, that is also possible. That is basically known as something called as self-attention. So in the self-attention scheme, what you do is that you run the RNN or whatever your model is on the input words. Then once you have run them on the input words, what you do is you do a self-attention layer, and the self-attention layer will update the input words themselves. For example, this word, it will be updated itself by taking into account what words it depends on, what words does it need to look at. So the self-attention block will update the hidden state of it and every other word in the overall sequence by basically looking at what it depends on and computing the self-attention matrix. Now, the advantage of this is that you not only have attention between your encoder and decoder, but even within your encoder, between different layers of RNN, you can have this self-attention operator, making sure that there is no forgetfulness happening. You can also build pure self-attention based networks instead of RNNs, and those are called as transformers. So in that case, only self-attention blocks will be stacked on top of each other without any RNNs coming in between. So in this case, what happens is that self-attention does not have any information about what was the position of the word. Like RNN has information like what word came before and what word came next. Self-attention does not have any information on position. So what we do is we give it something called as position encoding, wherein we tell it that this word is at position number 1, this word is at position number 2, this word is at position number 3. So we just one hot encode the positions and we give it into the encoder itself. This is one of the caveats of self-attention, wherein it is not position aware. So without position encoding, self-attention will not work. It will basically treat all the words in a sentence as a bag of words rather than a sequence of words. Now, the next thing to look at is how do you use those words themselves, like both in case of self-attention and in case of RNNs, how do you use the words? Like if you remember the previous example where we used and generated a character level model, we were generating characters and we generated HELLO, hello. So in that case, what happened is that we were one hot encoding each of the letters, right? But in case of words, the number of words is very huge. Like there are maybe more than 5 lakh words, like 500,000 words and more even than that. So basically one hot encoding words will basically mean that the one hot encoded vector will be very large, right? There will be one in one place, and then there will be like 500,000 zeros. So basically one hot encoding of words will not be very nice. So what we do is we encode the words themselves. We do a embedding of the word itself. And here what we do is we do a word level embedding. So each word will basically have one row in this big table. This big table will be 50,000 or more, like it will be basically the size of our vocabulary, or the number of words that we are ready to use in our model. It will be that long, that many rows, and the embedding size, which is the number of columns in the table, will denote what size of hidden state or what number of embeddings do we want to use for each word. So for example, here one word will be represented by this many columns. This will have basically arbitrary numbers which will be trained during model, and they will begin to represent the word as the model is trained further and further. So this way, when a word comes in, for example, this word comes in, then we will just pick this particular first row. When this first word comes advark, then we will just pick up this first row as its representation, and that representation here will be fed. So the first row, if the word here was advark, then the first row would be this, and that will be the representation of the word that will be fed in. Small details about these BERT and BERT models. So when this number of columns is 768, then it's usually a small or a medium model. While if it is 1024 or 1280, this number of columns, then it's a large model, and 1600 basically means extra large models. All right. So again, just showing you the representation here, and the token embeddings here are taken in this way. Like here you can see that from the first row, the token embedding is taken, then the positional embedding is taken, they're added together, and then they're fed into the self-attention models. Now I want to discuss a little bit about a important concept. So this is basically how BERT was trained, right? Google has developed a model called as BERT, which is also used in their search engine, and many other places BERT is used for various NLP tasks. Now, why is BERT so successful? So one thing BERT does is that it uses something called as self-attention blocks instead of RNNs, and that enables it to skip the forgetfulness problem. But that is not the only reason for success of BERT. There is a secondary reason for success of BERT, which is that BERT trains without any labeled data. Basically, you can train BERT on just plain text corpora without any labels. How does it do that? So BERT basically takes the task of predicting masked words. So you will basically take a sentence, for example, let's stick to improvisation in this kit. So you take this sentence, and what you do is you mask one or two words from this sentence. So let's stick to improvisation in this kit. You will mask it, and you will say, let's stick to mask in this kit. And now BERT model's responsibility is to predict what this mask was. What was the word which was basically hidden from it? It has to predict. Now, given that it is only predicting what word was hidden, so you can just feed it plain English sentences with word masking, and then you can use the loss function as whether it predicted the word mask properly or not, and then you can train BERT that way. So because of this, plain English text from Wikipedia and general internet was used to train BERT, and BERT was very successful because it was trained on large data and without needing any human labeling effort. So how do we use BERT? Let's look into that. We use BERT in something called as transfer learning setup. So in transfer learning setup, what we do is we find a model which has been trained on large corpora, and we then apply it on our smaller data set to basically get a good performance. So for example, here we say that in transfer learning, we find a similar data set, train a model on it and test it and apply it on our use case. So we need to find a similar data set. In this case, what happens in NLP is that we consider most of the texts as a similar data set to other texts. So we start with a model which is trained on Wikipedia and Reddit and general internet Q&A data sets. We train a model on it, which is BERT, let's say. BERT is very frequently used. And then we test it and apply it in our case. Like, for example, in our case, we can apply BERT models to sentiment analysis. We can apply BERT models to also do translation like work. But those models are pre-trained. So we are basically transferring their learning that they got on some text corpora via their pre-training, which was basically predict the word that is hidden from you. And then we use that pre-training knowledge in our problem statement by fine-tuning the model on our problem. And we will see an example of this on code and how it is helpful. So here is some more information about transformers. These links will guide you into both the mathematical details. For example, this one gives all the mathematical details of transformers, and some of these other links have also good illustrations to guide you through how the mechanism works overall. All right. So I am not going to discuss this. The general trend that has been in the industry is that if you have huge amounts of data, large enough data, then sometimes architecture is no longer important, but rather the data and the data quality becomes more important. And even a simpler architecture can actually outperform very complex architectures. So data quality and data quantity are important things to look at when you are solving a machine learning problem. And in case you can get more data, in case you can get better quality data, always go for that before going for improved architecture or more computation. Always hunt for data before you hunt for architectures and for more computation power. All right, so what did we see today? RNNs, we use them for modeling all types of sequences, videos, audio, machine translation, everything, right? Now, vanilla RNNs are simple and effective for short-term sequences, somewhere between 32 to 64 words, vanilla RNN can do. But if you have 128 or 256 words, then vanilla RNN will forget some of the words. LSTMs use something called as forget gate and a memory cell together to make sure that they can actually remember long context. LSTMs basically have 4 total gates, and all those gates work together to do this. Then we had also seen bidirectional RNNs, wherein you don't just need to look at the past, you can also look at the future to make a prediction. Basically, when you're predicting something like sentiment, or when you're doing machine translation, it's okay to look at the future, right? Like if you're doing machine translation, then you can look at the future words in the non-translated version. Like if you're doing English to French, then you can look at the whole English sentence from the past and the future, and then make the translation rather than looking at just the past and making the translation. Then we looked at transformers and transfer learning. Transformers and transfer learning are the direction that machine learning is going these days in NLP basically, and in sequence modeling also a lot. So attention basically enables you to skip the problem of keeping memory and remembering, because it essentially keeps the hidden state of all the tokens. Since you keep the hidden state of all the tokens in attention, you don't have to worry about forgetting. And it's kind of like looking back and referring to something and then improving your idea about what the overall thing is. So attention basically refers back to each previous word and then improves the representations gradually. Then we looked at transfer learning with pre-trained models. Pre-trained models like BERT basically are already trained on huge amount of a text corpora like Wikipedia, and we then transfer them to our own problems like small problems and sentiment analysis like problems, and they help us get a good performance. Next, we will look at a problem statement and see how we can solve it using transfer learning. As always, any questions you can ask in the Q&A after this session. All right, let's get into the lab session. So we will basically look at the recurrent neural network and compare it with transformers and how pre-training and transfer learning can help us. So we are going to work on this Jupyter notebook, and you can upload this notebook directly into Google Colab, or you can also use your own laptop or system, and if you have Jupyter installed, all the libraries needed are put here itself. And we are going to work on the GLUE dataset. Specifically, we are working on the Microsoft Research Paraphase Corpus dataset of GLUE, which is basically a dataset composed of sentence pairs, and it checks whether the sentence pairs are semantically equivalent. Basically, do they mean same or not? So before we get into it, I want to show some of the things here, important things. So one of the things is this device parameter. So if you have a GPU device, then this will automatically pick up the GPU device. Otherwise, it will pick up your CPU. So if you do it like this, then you can always just simply use this device parameter, and your code will be portable between CPU and GPU. It's very good for testing on your laptop and then deploying to a GPU device or to running it on a bigger cluster of GPUs. All right, so let's look at how the Microsoft Research Paraphase Corpus looks like. So you have this here, you just run this cell, just click on Shift Enter and it will run the cell. So Microsoft Research Paraphase Corpus MRPC is basically composed of 3600 train, 400 validation, and 1725 test cases. Today we are going to work with train and validation. Since the test set requires us to submit to a leaderboard, we will leave that for later. So let's check how the classes are distributed. So this has only two classes. Either they don't match or they do match. So 0 or 1. So we see that the class plot here shows us that more examples are of the matching type. Let's look at one particular example here. So it says that these two sentences are similar, and you can say that these do look similar, right? So, and there will be some which are not similar. So let's check that. Yeah. See the difference here. See, there's a major difference here, which is the valuation difference, which basically makes the major difference. And here, this is also a difference. So because of this, these two sentences are not semantically equivalent and the label is 0. So let's see how it actually does the overall thing. How do we make the model? So you take a tokenizer first. These tokenizers basically separate into separate words. A whole sentence is tokenized into separate words. So for example, here this separates this first sentence into basically tokens. This G denotes a word inside a sentence, and sentences, and the beginning of sentence is basically defined by words without this letter start. You can see it has separated all the words separately. After tokenization, so tokenization is this part. You can also tokenize and then make a numeric representation of the token. So that is being done here. So you get for each word a number basically. we will use these numbers to feed into our model basically, because words cannot be fed directly. Then we have some helper functions. This is for weight initialization. And then we have our model definition. So this is one of the important parts. We define two types of model for testing here. One is the RNN model. This is the RNN model here. The RNN model is nothing but a bidirectional RNN, and we'll specify some hidden sides. And the nonlinearity used here is ReLU. And then we also have a pre-trained model. This is the Roberta model, which is a transformer similar to BERT, and this is pre-trained on Wikipedia and other large-scale corpuses. All right. And then we do a forward pass in each step for training the model. So one of the specific things I want you to look at is this nn.module. You can subclass the nn.module thing and then make your model, and you will define a forward method in it. So that forward method basically takes care of how can one example be taken in with some labels and then loss be calculated. As you see at the end of the forward method, I return the loss and the predictions. All right, and you can also see that I am using this device parameter regularly, wherein I am pushing whatever inputs are coming into the device. Again, similarly, we have defined our evaluation function and our training function. The evaluation function basically checks for accuracy, and the training function is similar to before, and you can see that here in these steps the training happens. In these few steps the training happens, and one of the important points to note is that once we have defined the forward propagation, the backward propagation is taken care of by the framework itself. In fact, you can notice here that once I define the forward propagation in a particular way, the backward propagation gets taken care of by the framework itself, and then we train the framework. So we basically process the data set by concatenating both the sentences together, and then we feed the labels. So both the sentences concatenated together, separated by a separator, like here the first sentence is here, and then the second sentence is here. They're separated by a separator. This /s is the separator, and then we feed that with the label to the network. So let's look at how the network behaves. So first I try a RNN. So I try a RNN with two layers, 128 sized hidden. So basically 128 perceptrons in the hidden layer, and a two-layered RNN. I try that. And you can notice that RNN, when trained for 20 epochs with a particular learning rate, I have hyperparameter tuned this learning rate. You can see that it starts with around 35% accuracy in the first epoch, like here, and then it goes up till like 68% here, and it remains, it kind of hovers around on 68%, right? You can see that the loss is still decreasing. So why don't we train it further? So I did that. We trained it for further, and you can see that here it remains at 68%, while the loss decreases. The loss is 0.674 here, and by the end of this stage the loss is quite low. It is 0.64 instead of 672. So loss has decreased, but the accuracy did not increase. I decided to train it even further, and for 20 more epochs, and what I see is that the accuracy still remains the same. The loss also stagnates finally. So we are able to get somewhere around 68% accuracy using the RNN, which is not a pre-trained model. Now let's use a pre-trained model, a Roberta pre-trained model, and see what we can get. So for this Roberta pre-trained model, I will only train it for 5 epochs, and we will see the results. So here it starts with 68%. In fact, in the first epoch itself, it has hit the accuracy of the RNN. In the second epoch, it stays similar. In the third epoch, it's already 80%. And then it hovers around in that range, 78 to 80%. So you can see that it started here, went down, hovered a little bit here, and then again further went down. It is very much possible that further training will reduce the loss further and give us more accuracy. But you can see that even without further training, with just 5 epochs compared to RNN's 80 epochs, it is able to reach 78% accuracy because it's a pre-trained model. The total training time on my hardware was 11 minutes for this model. And for RNNs combined, it will be, let me check and tell you. RNNs, it was around 10 minutes. So basically 11 minutes of pre-training here and 10 minutes, 11 minutes of training here, 10 minutes there in RNN, but this performs much better because it's pre-trained on a large text corpora. So that concludes our lab for RNN and also our overall session on RNN. Feel free to ask any questions you have about RNN, multi-layer perceptron or CNN in the Q&A session that will be coming next after a small break. And hope you had a great learning experience. Hope you were able to learn well and deeply about RNNs through this session. Thank you.